All right. Well, hopefully you found that interesting. The idea that she couldn't even recognize her own mom's face is showing you that there is something special about recognizing faces. If she hears mom's voice, or if she can see the hairstyle, or she can see the clothing, then she can make a decent decision, right? But if you have to rely just on facial features, prosopagnosia shows us that there's a part of the brain that does this kind of synthesizing of the elements of a face and determines that it's a face is one big broad analysis that has to happen. And then familiar, unfamiliar, age, sex, these factors get processed in this very quick, broad analysis. And then you synthesize all of those factors into one coherent sense of this face. All right, so some features of the analysis by synthesis model. First, you break the stimulus into its component features. Now, I'm going to give you a non-face example of this, the Mueller-Lyer illusion. This is something from the Gestalt theorists, so very early German researchers, and they showed people pictures like this. You've probably seen this before, where you are asked, which one of these looks longer? And for most people, they'll say the one on the right looks longer. And so I've heard people say different explanations for it, not psychologists, different people say different explanations for why the one on the right looks longer. They'll say things like, oh, the outward facing arrows draw your eyes out. Or if this were rotated on its side, they'll oftentimes say, well, the one on the top looks longer. All sorts of incorrect explanations of what's going on. First off, let's establish that this is a perceptual error that we're making and not a sensation error, because I went ahead and drew red lines over it, and now I'll animate them and show you that those lines are exactly the same length. So just to clarify, these are in fact the same length. What your eyes are collecting, what the sensation is reporting to your brain is accurate. That in fact those two images, the one with the closed arrowheads, the one with the open arrowheads, those are the same length. So we've established those are the same length. So now why would we mistakenly feel like the one on the right, why would we perceive the one on the right to be longer than the one on the left? Well, think about how the world is designed, right? Look around your own house and you'll see that there are some edges that are closer to you and some edges that are farther away from you in a three-dimensional world. So in this particular drawing, we have, I drew a red line over the receding corner on the right. Over there by the door and the window, you see there's what we call a receding corner. And look at how that receding corner appears. You have the straight line that I put the red line over, and then you have those outward-facing arrows, just like you do in the Mueller-Lyer illusion, right? See how they're making those V's, the upright V and then also the upside-down V? And then when you look at the red line on the left, it's not quite perfect because we're highlighting the window in this picture rather than what I would have liked to have done with this picture, which would have been the protruding corner. But let's just look at the window. It's got half of what you see in the Mueller-Lyer illusion on the left-hand panel. What you see is you've got the straight line, and then you've got what appears to be, I guess you'd call them the closed arrow at the top and the bottom of the window. See how the line of the window, because it's coming towards us, the leading edge looks longer, and that causes that sort of angled top and that angled bottom of the window. If we had been using the corner of the wall that's just directly to the left of the window, you'd see very clearly at the top where the wall comes into contact with the ceiling, you see those arrows that look just like the left-hand arrows in the panel A. And at the bottom, you see the same closed arrow down there. Those kinds of experiences in the world have taught you that typically if the line is the same length landing on your retina, one of them appears to be a leading corner and one appears to be a receding corner. Your brain tells you, well, the receding corner, it's looking the same length, so it must actually be longer because I know it's farther away from me. This is depth perception, right? I know it's farther away from me. And so our brain makes that correction even though it's an incorrect thing to do right now, right? So our two red lines that I had used to cover those are in fact the same length. But our brain says the one that's, because it's the same length, because what's landing on my eye is the same length, and I know it's farther away, it has to be longer. In order for it to appear the same length to me on my eye, on my retina, it has to be farther, it has to be bigger. I know it's farther away, it has to be bigger. Your brain makes these calculations. And so it breaks these into these small parts, and you're drawing inferences as you move through the world, trying to make sense of what is being presented to you. So with regular objects out in the world, not just faces, but with regular objects out in the world, you do break it down into these elements and then perceive it as a whole, right? So I broke it down into these lines, that's elements, right, components, and then, but you're in the context of depth in panel B, right? You're in the context of something farther away from me. And so this analysis by synthesis means that we break it down in our component features and then we bring it back together in order to synthesize it and make sense of it. This model agrees that there is a feature list stored in long-term memory. It's not a template where you have intact objects, it's features that are stored in your long-term memory. So in this model, you don't have to search through every template for a glass. You can just look for features that are characteristic of this glass and figure out what the object is from that. The fact that we have feature detectors in our cortex really supports this theory. The fact that we have discovered individual like cells, I say like cells because sometimes it's a little group of cells that are firing together in response to a particular feature. But the fact that we have found cells in your visual cortex that only respond to certain features kind of supports this theory, right? Now, what do I mean by certain features? So here we have 3 panels. The one on the left is vertical lines, the one in the middle is diagonal lines, and the one on the right is horizontal lines. These are already kind of out of focus because I really blew up the picture to make it fit on the slide. It lost all of its sharpness. But so in real life, they would take a small piece of paper that has these 3 panels in focus and tape it on the wall and ask participants to back up until one of these panels was out of focus for them. One of them has lost its sharpness. And in the US and other, I'll call them carpentered kinds of environments, people stop, they say something has gotten blurry, and then what they say has gotten blurry is the middle one, the diagonal line. The diagonal line got blurry faster for people who were raised in a carpentered world. If you apply this same exact test, which they have done to Australian Aborigines, all 3 panels become blurry at the same rate. You know, they're living in the outback, they don't have a carpentered world, all 3 panels get blurry at the same time. So what's going on? We have feature detectors that are designed to detect vertical lines, diagonal lines, and horizontal lines. If you're raised in a carpentered world, you see a lot more vertical lines and horizontal lines than you see diagonal lines. I mean, houses have gable and roofs that are diagonal, and you know, there are diagonals in the world. So obviously we can see diagonals even if we were raised in a carpentered world, but we can't see them as well as we can see horizontals and verticals. If you were raised in the Australian outback without a carpentered world, you can see all 3 to the same degree, but none of them as well as a person who was raised in a carpentered world can see verticals and horizontals, right? Like all 3 of them become blurry at the same time, and more like the diagonals get blurry for people who are raised in a carpentered world. Because if you were raised in an uncarpentered world, you don't see that many purely vertical and purely horizontal lines or purely diagonal lines. You don't see a lot of any of those things. Everything's a lot less straight, let's just say. So, and your experience in the world helps to determine the actual format of your feature detectors. So you will use those same cells that are available to be feature detectors to see more. If you see more of these kinds of stimuli, you're going to want more detail on those stimuli. You see a lot of it, and so you want to devote more brain cells to that kind of stimulus than to things that you don't see as often. And so we see that in people who are raised in carpentered worlds, and they see this in animals also. If you raise them in an all vertical world where they're living in a cylinder with no horizontals, and no diagonals, everything's vertical. All of their visual feature detectors are going to be devoted to processing visual vertical stimuli. Your brain adapts to whatever you've experienced is the basic premise. So I thought it'd be fun, since I wanted to make sure that you knew about these feature detectors, to share with you this video about Hubel and Wiesel discovering feature detectors in cats, and they discovered it purely by accident. So I thought that was kind of interesting. So go ahead and watch that, and I'll see you on the other side.